Settings for the F7 series Nucleo boards. Hello and welcome back to the lecture, and in this lecture I will show you how to configure lwIP for a STM32F7 series Nucleo board. So right now in my hand I have a STM32F7 series Nucleo board. So the chip here is STM32F756. And previously I have used a Nucleo board that was based on STM32F4 series. But this time we are going to use a board that is based on STM32F7 series. So let us begin. So the very first thing that Cube IDE will ask you when you create a new project is this. That is, for this Cortex M7 device, it is highly recommended to pre-configure the memory protection unit or MPU to optimize speculative read access of the core. And here you have to select yes, like this. And after that, most of the steps are identical to what we have already covered in the video for STM32F439 series. And in this video I will only discuss the steps that are different from STM32F439. So first we have to do some system settings. For that we will go to this section, that is system core, and here we have a new item that was previously not present. So in the case when we are using a M4 based processor, this option was not there in this Cube IDE. That means under system core we didn't had the Cortex M4 settings there. But in the case of this new board, that is STM32F756 base board, which has a ARM Cortex M7 processor, we have this option here in the Cube IDE. So first we have to go inside this, and here the first thing that we have to change is the flash interface. By default this flash interface is AXI interface. We have to change this to TCM interface, or this TCM, it stands for tightly coupled memory, a memory that is tightly coupled to the core. We will use this interface, and when we use this TCM interface we have ART accelerator enable, which makes instruction fetching from the flash memory very fast. And we also have this instruction prefetch enabled. Right now we will keep these two cache memories disabled. And then about the memory protection unit, the MPU control mode, it will be default like this one. So here we have by default this option selected. We don't have to change this option, nor we will make any changes to these memory protection settings, region settings. We won't touch this region setting. By default it is set up something like this. So only one region is enabled for MPU, and this region contains entire addressable memory range for this processor from 0 to 4 GB, and it is set up something like this. So we will keep the default settings here. Next we will go to the RCC section and do settings like this. I have already discussed this. And after that we will move to the sys section, and here we will choose serial wire as the debug interface and TIM6 as our time based source. And after that we will configure FreeRTOS, and in the previous video I have discussed everything in detail. Then we will need to do the clock configuration, and here we need to do settings so as to get maximum clock speed of this microcontroller. So by default you can see that our microcontroller, the main clock is set to 16 megahertz, which is very slow compared to the maximum that it can support. And the maximum that it can support is written here, that is 216 megahertz. So we have to configure everything so that we get maximum clock output for our microprocessor, the CPU of this microcontroller. So first we have to do a change here. The input frequency is 8 megahertz, and this is mentioned in the user manual of our Nucleo board. And then we need to change the source of this PLL. By default it is HSI or high speed internal. We have to choose this one, that is HSE or high speed external, because we are using a clock source that is coming externally to this microcontroller, and this clock is coming from the ST-Link unit of our development board. And then we need to change this, that is the system clock source. It is coming from directly from HSI or high speed internal. We have to change this multiplexer and select this one, that is PLL clock, so that our microcontroller is clocked from PLL and not from the HSI. and then I will make some changes here. I will choose this divider, that is PLLM, to be by 8. So I am getting a 8 megahertz input and I will divide it by 8 to get a 1 megahertz here, and then I will multiply it by 432 and then divide by 2 to get 216 megahertz here, like this. But we still have some problems here, and this problem are with the peripheral clock or the peripheral bus. So this peak clock 1, which is going to the peripheral bus 1, the maximum is 54 megahertz, but we are feeding 216 here, so we have to choose a proper divider here. Now it is great. If we divide 216 by 4, we will get accurate 54 megahertz. That is the maximum speed of this peripheral bus. And secondly, we will change the second peripheral bus, which is getting clock from P clock 2 or peripheral clock 2. So the maximum is 108 megahertz. So we'll divide this incoming 216 megahertz by 2 to get an accurate this one, that is 108 megahertz. That's it. Our clock configuration is finally done. Then I will again go to the pinout and configuration section, and from there I will enable the UART, and it is under the connectivity section. I will enable UART 3 here. Note down the baud rate. Right now these two pins are assigned to UART, but I will remap them to PD here, because in our Nucleo board these pins are connected to the UART or the inbuilt USB to serial converter. Now we'll move on to configure the most important peripheral, that is the Ethernet peripheral, and you will find Ethernet peripheral under the connectivity section here, ETH. But now I will highly recommend you to go and watch my previous video in which I have discussed all this step for the STM32F4 series processor. So all the steps are same, I will only discuss the differences. So let me choose RMII here. And what is this RMII and more thing? I have already discussed in great detail in my previous video. So please go and watch that video before configuring this peripheral. I am not going to repeat all those things here again. But if you have a look here, things have changed. That means this GUI has changed a bit. So in the F4 series, this GUI was bit simpler and there were fewer options. And in this F7 series, we have more options, which might confuse you, but don't worry, we will discuss everything in detail in this video so that you can easily configure your F7 based microcontroller also. So here I have a screenshot from my previous video and you can see the configuration like this. It was available in case of the 439 microcontroller, which is based on STM32F4 series. So this is the settings for F4 series. So let me zoom into this portion and show you the differences. So now I have both the screenshot and my actual STM32 cube ID. So here on the right I have the screenshot from my previous video, and here I have the actual STM32 cube ID. Now we can easily compare the differences here. So we can see that in case of STM32F4 series the configuration was bit simpler, and here in the case of STM32F7 series it is bit more complex due to more options here, and these options are related to the RX and TX descriptors, and I will not explain what are these descriptors. I will have a dedicated video for them. Here I will only show you the basic configuration that will help you make a working project. So here we can see that previously we only had the option to configure the Ethernet MAC address, and presently we are also having that option, that is Ethernet MAC address. So here we have to put our MAC address. So consult the previous video how we have to enter a MAC address here. And then we have TX descriptor length, which is by default set to 4, and this default value is very good, we don't have to change anything. And then we have the first TX descriptor address, and this address is also proper and valid, we don't have to change anything. I will explain about this address. Then we have the RX descriptor length, which is also set to 4, and this is the default value and it is good, we don't have to change this. Neither we have to change the RS descriptor address. This one is the RS descriptor address. Then we have the RX buffer length, which we also had previously also, that is RX buffer length here. The default value in case of F4 series was 1536. but this time it is 1524. So we'll not modify this value, we will go with the default one. Then we have this RX mode. We also have RX mode here also, and in this RX mode we have to select this one, that is interrupt mode, and you can get the hint from here, RX mode. And when we use FreeRTOS we have to use this one, that is interrupt mode. That is why we are selecting interrupt mode here. And to understand these settings completely, I mean about these addresses and everything, we need to have some background knowledge about the architecture of this microcontroller, the architecture of the Ethernet controller that is present inside this microcontroller, and also the architecture of the lwIP TCP/IP stack, especially the memory management part. But before we dive into that, let us first enable lwIP from the middleware section. Enable it from here. Now if you compare these settings with our previous project, you will see a bit of difference here. So this item is extra here. So in case of STM32F7 processor, we have this extra option in our STM32 Cube ID, this GUI configurator. So here I have the screenshot of my previous project, the project that was based on STM32F4 series. So here you can see that inside this infrastructure heap and memory pool section, we have only two options. The first one is the MAME size and the second one is the ETH RX buffer count. But this time we have this extra option, that is lwIP RAM heap pointer. But here I would like to tell you about a bug in this version of STM32 Cube ID. So this is the version that I am using. It is 1.17.0. So this version of Cube ID, it has a bug here. And what is the bug? The bug is this memory address where the STM32 Cube ID is trying to locate the lwIP's heap. So actually this default value of this address where it is trying to locate the heap, it is an unimplemented location in this processor. We do not have anything installed in this memory address. We don't have any SRAM or anything. So if you build this project, it will cause a crash of this program and you will land into a hard fault. And it is very hard to debug what is the problem, but I have found out that this is the root cause of that problem, and I'm sharing the solution with all my students so they don't get frustrated and they get their project working in the first trial itself. And I have also posted this issue in ST's forum here. So now here I am in the official forum of ST Microelectronics, and here I have created a topic that I am facing this problem with this heap pointer. So they have confirmed, and ST employee has confirmed that this is the issue in this version of Cube ID, and they have also opened an internal ticket for this issue, and this is likely to be solved in the future release. So let us see what happens in the future. But if you are using this version of Cube ID, that is the latest version of Cube ID, you have to create a workaround for this, and I will discuss the workaround. So let us first open the datasheet and the reference manual of this microcontroller. And here we have, this is the reference manual and this is the datasheet. I have opened both the documents here in my PDF viewer. So first I would like to take you to the description section here, and we will scroll down a bit, and here we can see the comparison of various features present in various different variants of this microcontroller. So right now we are interested in this thing, that is the SRAM. So here you can see that our microcontroller, the microcontroller that we are using, all the variants, they are having 320 kilobytes of RAM or SRAM, static RAM. But the interesting thing is this, it is split into three parts. That is why they are showing a detail here, that is it is actually 240 plus 16 plus 64. So the actual SRAM of this device, it is divided or split into three different types. So this first one, 240 KB, is the main SRAM or the SRAM 1. Then we have another SRAM, and this is called the SRAM 2, and this is very small, only 16 KB. And finally we have this one, this 64 KB. This is a core coupled RAM or ARMS tightly coupled memory. But now the question arises, why there are so many different types of SRAM? So let us investigate that. And this is done mainly to increase the complete throughput of the system to get maximum possible performance out of this microcontroller. So let us go to the page number 19 of this data sheet, and here you will find the AXI AHB, that means the high performance bus matrix architecture. Now what is this bus matrix? So this bus matrix is required because we don't have a single slave in our bus. In traditional microcontrollers, there was only one master present on the bus, and that master was the main CPU, and the other memory devices and peripheral devices were its slave. But in modern microcontroller, it is not the case because there are several masters also. So mainly these masters are the DMA or the direct memory access. So they can also read from the memory, they can also write to the memory, they can read from the peripheral, they can write to the peripheral, just like a CPU. And these DMAs are used to quickly move data from peripherals to our memory without any CPU intervention. But there is a catch in that. If both the CPU and the DMA try to access the same slave, then it is not possible to simultaneously access a same slave from two different masters. But this bus matrix, this magical bus matrix, it allows simultaneous or concurrent transfer between separate masters and slave. So let us try to understand this with an example. So here is our Cortex M7 CPU, and here we have few slaves, and one of them is SRAM 1 and the SRAM 2 also. So we can see that the main SRAM is divided into two parts, the SRAM 1 and the SRAM 2. So this is the main SRAM, which is of 240 KB, and the second one is of only 16 KB. So we can see that there are two different separate slaves on the this bus matrix. So for example, here we have our Ethernet MAC. So for example, here we have our Ethernet MAC, and suppose it is receiving some data through the RJ45 connector or the LAN or Ethernet cable. It is receiving data at high speed from external world or the external network. So now all the data can flow from our Ethernet MAC and through this bus matrix, and we can make it to flow it to this SRAM2 like this. And while the Ethernet DMA, this Ethernet MAC, it has integrated DMA for its purpose because it is a high speed peripheral. So it has a dedicated DMA for itself and it is integrated inside this. We don't have to use any of this GP DMA. This GP stands for general purpose DMA. We don't have to get help from them. It has integrated DMA which can transfer data from its internal FIFO buffer to any of the user RAM. So in this scenario, data is flowing using this route, and now the CPU is free. It is free to communicate simultaneously. At the same time, the CPU is able to access this SRAM2 through this channel. You can see our CPU can access this RAM. So this data flow will be completely parallel to this operation of the CPU. So this data flow will not hinder the data flow that is done by the CPU. For this reason, they have split the RAM into two parts to allow true concurrent access through this DMA. So in the lwIP's dynamic memory management system, mainly we have two types of memory, and the first one is the heap memory and the second one is the pool memory. So what is the basic difference between these two, that means heap and pool? You all must already be familiar with this heap memory. This is the normal type of dynamic memory that we can allocate using the malloc function, and since this lwIP is designed to be run on small embedded system, it does not expect have a memory manager already present in the system. That is why it provides its own customized memory manager, dynamic memory manager. So it has its own memory allocation functions like malloc, but it is actually implemented by the internal memory manager of lwIP. While this pool memory, it is a special type of memory. It is actually statically allocated pool of predetermined size. So we already pre-allocate certain amount of memory as static memory of the data structure that we need, and this pool manager, it help us to get one of those data structure from that pool, pre-allocated pool. So the allocation and deallocation using pool memory is very fast and it is deterministic, while this heap memory allocation and deallocation, it is not deterministic and it is not fast enough. So generally this pool memory is used to allocate memory from inside ISRs or interrupt service routines, because we need faster performance and deterministic performance from inside an ISR, while generally this heap memory is used to allocate memory from user level tasks. So generally LWIP uses this pool memory for incoming packets and it uses this heap memory for outgoing packets. So whenever we try to send something through LWIP, it allocates the packet using a heap memory and then places the data in that memory for transmission through the LWIP stack. While on the other hand, when we have an interrupt from our Ethernet controller, any Ethernet controller, whether it is internal or external to the microcontroller, we generate a ISR or interrupt service routine that a new packet is received by our Ethernet controller, and in that case LWIP uses a pool to allocate memory for the incoming packets like this. The pool memory is fast and deterministic, but it has a disadvantage. It wastes lots of memory because it considers the worst case scenario for pre-allocation. So we have a pool of packet, received packet, but we have to consider the worst case scenario, and they have considered the maximum size of the Ethernet frame for each pool. So even if the incoming Ethernet packet is very small, it will always allocate a maximum size memory for that incoming packet. And in case of Ethernet frame, the maximum size is 1518 bytes. So they generally allocate this much amount of memory pool, that is 1518 bytes, and multiple such pools, for example 12 such pools. So let us calculate how much memory it will waste. So inside this key option setting, under infrastructure heap and memory pools option, we have this option, that is ETH-RX buffer count, and it is set to 12 by default. So this is the number of slots that is available in the RX pool, and each of these 12 buffer is approximately 1500 bytes long, or the size of a Ethernet frame or maximum Ethernet frame. So this pool will require 1518 multiplied by 12, this much amount of RAM, or it is approximately 18 KB of RAM only for the RX pool, and still we need some space for the heap memory. So if you are not able to understand all these things very clearly, please don't worry, as this video is not dedicated to dynamic memory allocation of LWIP. Of course we will have dedicated lessons on those topics, that means dynamic memory allocation in LWIP, and in that chapter, in that video, I will discuss all these things in great detail. That means the heap memory, the pool memory, everything in great detail. But the basic idea here is to fit all the memory required by the LWIP stack or the Ethernet peripheral in SRAM2. Here in the SRAM2, 16 KB SRAM2, so that we get maximum performance out of this configuration. So mainly we saw that we have two different types of dynamic memory under LWIP. The first one is the heap and the second one is the pool. So we will try, our aim is to fit the pool and the heap inside this SRAM2. But sadly this is not possible in this microcontroller because the SRAM2 is very limited, only 16 KB. And the 16 KB will be used up only by the heap memory, and we were left with no more space for the pool memory. So in this microcontroller we can only put either the heap or the pool inside SRAM2. We cannot fit both of them inside SRAM2. This is the problem. But with certain high-end microcontroller like STM32F7 series, we have lots of memory available here in SRAM2, and under those microcontroller we can fit both the heap and the pool memory inside SRAM2, but we cannot do that with this F7 series. So in this microcontroller we will only put the heap memory inside SRAM2, while we will keep our pool memory in the normal SRAM1. So let us first open the reference manual and go to this section, that is 2.2.2, the memory map section. And here we have to find the starting address of SRAM2. So here we have our SRAM2, and from here we can see that it is starting from this location, that is hexadecimal 2004 and then C000. Our SRAM2 is starting from this location and ending at this location. So we will keep three things inside this SRAM2. First one is the RX descriptor, second one is the TX descriptor, and the third one is the lwIP heap memory. So let us go to our STM32 cube ID and then go to the Ethernet peripheral configuration under connectivity section like this, and here we have the RX descriptor and the TX descriptor. So in the default configuration, our RX descriptor length is 4 and TX descriptor length is also 4. Again, please don't worry if you don't understand what are these descriptors. We will have a dedicated lesson on those things. Here you just have to understand one thing, that these descriptors, that each of these descriptors are 40 bytes in length. So let us also confirm this fact. So for that you have to go inside this section, that is lwIP. Here the top level lwIP folder, then target, then Ethernet interface. So here you can find those descriptors. You can search for them. So here you can find the declaration of those descriptors. But here they have a lot of conditional compilation for different compiler. So this first one is for ICC compiler, ARM compiler, IAR compiler. But as we are using this STM32 cube ID, which internally uses the GCC or the GNU compiler collection, we don't have to look inside this conditional block. That means from this if to this else if. And this is for the MDK compiler. Again, we are not using MDK compiler, we are using this GNU C or the GCC compiler. So here we have to look, and so these are the structures: DMA, DSC, type def. So if you hold the control key on the keyboard and then click on these, it will take you to the actual this declaration of this structure. So how this structure looks. So this structure is composed of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 of these registers, and each of these registers are 32-bit long or 4 bytes long, and we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10 multiplied by 4 byte, we have this, the length of this is 40 byte, as I have already told you. So let us go back to the Cube MX view or the GUI configuration view. So here have a look that the first RX descriptor is kept at this location. And if you remember, this is the starting location of SRAM2. Let us also match this address once again. So it is 2004, 2004, and then C000, C000. So the very first thing that is placed at the starting of SRAM2 is the RX descriptor. And how much RX descriptor we have? We have 4 of them, and each one of them is 40 bytes long. So total amount of space that is taken is 40 multiplied by 4 or 160 byte. So let us convert this 160 into hexadecimal. So we have this value, that is A0. So we have to add A0 to this value to get the end of this block, and that's what we are using here. So it is 2004, this is same as this 2004, and then C0 same, but we have added A0 to this, and this marks the starting of TX descriptor. So in our SRAM2, we first have our RX descriptor, and then exactly after that we have our TX descriptor, and the TX descriptor is also 160 byte. Complete size is 160 byte, that is 40 multiplied by this 4, we have 160 byte. So we have to add 160 to this address to get the end of this block. So let us do that. Let us add 160 more to this, and we will have a hexadecimal value of 140. So we have to add 2004C0 plus 140 to get the end of this block, and it is coming something like this. Hexadecimal, that means 0x, then we have 2004, then we have C, and then we have to add this one 140. So this is the ending location of this TX descriptor, and from this address we can begin our heap memory. So let us copy this value and then go to this configuration, middleware section, lwIP, and here where I have already mentioned that this value is wrong, so we have to get rid of this value like this and put our calculated value here. So previously it was an invalid value that was causing a hard fault, but now we have fed here a proper value, we know that the SRAM2 exists at this location, so this time it should not cause any crashes or hard faults. And after that we need to do one more setting, and this is the size of the heap. So by default our cube ID has chosen 1600 bytes for this, but this is too low, so we must increase this value, and I will increase this to 16,000 bytes like this. So this is near about 16 KB, which is approximately the same size as the size of our SRAM2. But while setting this option, please make sure you don't overflow SRAM2. So let us confirm that using my calculator. First we will calculate how much is 16 kilobytes. It is 16 multiplied by 1024, because in 1 kilobyte we have this much bytes, or 1024 bytes. So in total we have this much bytes in our SRAM2, that is 16,384 bytes. So let us subtract the amount of memory that is required by the descriptors. So I have already discussed that each descriptor is of 40 bytes, and we have 4 RX and 4 TX descriptor. So in total we have 8 descriptors, each of 40 bytes. So in total we are consuming 320 bytes. So let us subtract 320 from this. So we are left with this much byte, that is 16,064 byte. So you must not enter a value greater than this value in this area. And right now we are putting 16,000 here, so we are not overflowing our SRAM2. Now we are all ready to generate the code. So we'll go to this option, that is generate code. Device configuration tool, code generation. Let us hit this button and generate the code for us. Please wait for a while. Now the STM32 cube ID has generated all the code for us. You might be excited to build this code right now and test your project. But before that we have to do a little modification, and this time we have to edit the linker script file, or this LD file. So here in our project we have this file, that is STM32F756 GTX flash.ld. We also have a ram.ld file, but this one is not used. This is used when we want to execute our code from RAM. So this one is currently shown in bold, and this one is currently used because we are executing our code from the flash memory and not from the RAM. And here we have to do a little modification. So by default the code that is generated by this cube ID, it has only two sections in memory. One is RAM and another is flash. So all the three different types of RAMs are merged together here in this RAM section. So here we have to do a little modification. We have to create one more section especially for SRAM2, and for that first we have to reduce the size of this thing, that is RAM. So by default it is the addition of all these three, that is 64 plus 240 plus 16. So we have to remove SRAM from there. That means we have to subtract 16 from this value, that is 320, and we will get 304. So I will make this section smaller like this, and then I will add another memory section like this, and this time I will name this section as SRAM2. and we will put the origin where SRAM is starting. This SRAM2 is starting. You can get the starting address from here. This one 2004 C000. So same I have fed here, that is 2004 C000. So this will create another memory section specially for this SRAM2, and the length will be like this 16 kilobytes. And now we have to go to the end of this file, that is the LD or the linker script file. And here I will specifically create a new section for lwIP like this. So you can copy paste my code. I have marked it like this: modification start and modification end. And here I am creating a new section called lwIP section. This SEC stands for section in short. And there inside I am creating two more sections like this. One is the RX descriptor section, and then we have the TX descriptor section. And this RX descriptor section is starting at this address. So same value that we have used in the GUI, you have to put here also. Let me show you. These values that we have used here while initializing our Ethernet peripheral, same value for the RX descriptor you have to put it here, and the TX descriptor address, this one you have to put it here. And finally we have the lwIP heap section. Like this we have to create memory section, because the compiler that we are using currently, that is GCC, it does not support placing objects directly in a particular memory location. But other compilers like Keel compiler or IAR compiler, they support direct placement of objects in specified memory location. So in that case you do not have to edit the linker file like this. So why we need to do this modification, let me explain you. So for that, just open your this top level lwIP folder, and from there go inside target and Ethernet IF, and there search for descriptors like this. So here somewhere around this line 100 they are declaring the descriptors. And I have already told you that this contains lots of conditional compilation for different compiler, and we have to put our attention here in this else if section, which is for our GNU C compiler. So they are using this method. So this is the actual data type, the structure, and this is the identifier for this variable. So as you can see, these are array type variable, and it is having this much count. 4, we have already set 4 here in the GUI, you must be remembering. So this 4 is 4 and 4. So these are coming from here on these constants like this. And after that, so this is the array, this is the descriptor, these are two array, and they are using this attribute, this thing, to place these variable, these two array in the particular section. They cannot specify the particular address, but here if you see the code for this Keel compiler, they are directly able to use this pragma hash pragma location to put this variable or this array in this particular locations. So we don't have to edit the linker script file. And same is the case of this Keel MDK compiler. It uses this attribute, so at attribute. So using this at attribute, they are directly able to place this array in this location like this, and this array in this location. But we cannot write such code directly using this GNU C compiler. It only supports specifying a particular section. So they are not using the directly hard-coded memory addresses like this, in case like they are using in case of this IAR compiler or this MDK compiler. Rather they are placing this variable in particular section. So they are using attribute and then section, and then they are specifying that this DMA RX descriptor tab should be placed in this section, that is .rx descript section. And the same, the TX, this array should be placed in this section, that is TX description section. And we are doing that exactly using this linker script. We are creating these two named section like this, so that our variable could be placed on those section. So that's it, this much modification we need. Now we are all ready to build and test this application. Now let us try to build this project. So I have hit the build button here and my build is in progress. Like this, we have to wait for some time. And in the meantime, you can take out your development board, that is the Nucleo development board, and connect it with your PC using a USB cable so that everything is ready for debugging. So here it is, our build is completed with 0 errors and 0 warning. But before executing this code, let us first go to this section, that is the build analyzer. And here hit the refresh button. So what I would like to show you here is that whatever changes we have done in our linker script file, it is reflected here exactly. And because of our modification, we have this new region in the memory region section. So before that, we only had this RAM and flash. But now this new region is also here that we have created, that is SRAM2. And we can confirm the start address, the end address, the size, everything. So let me first maximize this window. And here we have, and now if you go to this section, that is the memory details section, here also you will find the detail about each of the memory region. So here we have our SRAM2 and inside this you can see our lwIP section as we have created in the linker script. And you must also confirm the location. So here we can see that the location is perfect, it is 2004C000, that is the start of SRAM2. And we can also find our DMA descriptors here. So first one is the RX descriptor and second one is the TX descriptor. So these two variables or these two array variables are placed at the correct location. But still this project contain a little bug, and this bug is due to this cube ID, and I will discuss it in a moment. So now let us start a debugging session and see what happens. So here is my debug button, let us hit this button and start a fresh new debugging session. Waiting for debugger connection. Debugger connected. And now it is downloading the code to the flash memory. Download in progress. Verification. Download verified successfully. And now my debug session has started. And this, you can see this blue arrow in the very first executable line of this main function. And now we are all ready to hit the resume button to run our code and see what happens. So now let us hit this resume button. Now our code is executing. But now let me show you the bug. For that, first pause this program. And from this window, go to the show view. And from there, free RTOS. This is the second one in the menu, and from there enable the task list view. And here we have our free RTOS task list view. So let us analyze the stack usage of each task present in our application using this tool, that is the free RTOS task list view tool. So from here we can see that the first thing, that is the default task, the stack usage level is 54%, that is okay. Then the second thread, that is the Ethernet IF thread, it is using 59%. Then we have ETH-link thread, it is consuming 25% of its allocated stack memory. Then we have the idle task, it is using 18%. Then the main TCP IP thread, it is also using 36%. So everything seems alright, no problems here. And finally we have the timer service task, and it is also consuming only 16%. So everything looks correct. But this is the case when I have not yet connected my Ethernet cable to the RJ45 connector that is present on my Nucleo board. So you should also do it the same way. Please don't connect your RJ45 cable. Just run this program without connecting the RJ45 cable, and let us see what happens when we connect the cable. So now I'm going to connect my RJ45 or the Ethernet cable to my Nucleo board's RJ45 connector. And but first let us resume the program and then connect the cable. Now I have resumed my program and now I am going to connect the cable. Connected. And after connecting the cable, let us pause the program once again using this suspend button. Now let us analyze the thread and try to find out the problem. So here you can see all the threads are okay. This is 54%, 58, 18, 44, 16. The problem is here. This is 100% uses, and this one is the Ethernet IF thread, and this thread has already overflown its stack. It is not only consuming 100%, but it has already overflowed. So this is the error condition or the bug that I was talking about. So if you try to ping your board, it will come no destination host unreachable like this, and your program will not function as expected. So this is the major bug in the STM32 cube ID. It has selected a wrong value for this stack size of this thread. So we have to increase the stack size of this thread, that is eth link interface thread. So now let us do that. So let us go back to your project, and under this section or this folder, that is the top level lwIP folder, expand this, go to target and Ethernet IF, and here you have to find that thread. So just hit Ctrl plus F to open the find dialog, and then search for like this. So here they are initializing that thread, and to understand this code you have to be familiar with the CMSys version 2 OS API, and they are creating a new using this OS thread new function, and this is the here they are putting a meaningful name for this thread, and using this name only we have identified that this thread or this task is having the stack overflow problem. So we have to increase the stack size, and here you can see that they have specified the stack size using this constant. So let us go to this constant. Here is the constant. So this value is very less, we have to increase this value. So let us increase this to 1 kilobyte or 1024 bytes like this. Now let us once again build this project and run this project, and let us see what happens this time. This time I am keeping my Ethernet cable or the RJ45 cable connected to my Nucleo board, and I will run the program. And then after some time, let me pause the program and analyze the stacks. So see, this time we have increased the stack size of this ETH-IF thread to 1024 byte, and this time with the cable connected it is taking only 388 bytes. So last time the default value that cube ID has used was 350 byte, but the actual requirement is 380 or 390 bytes. So definitely that value was wrong and it was causing problem with our program. So when we have increased the stack size, now it will work perfectly. So now let us see. Now no thread is overflowing, every thread is working properly. So now let us resume this program using the resume button, and now let us go to our terminal and try to ping our embedded host like this using the ping command, ping, and then the IP address of our embedded or the STM32 host. And as we have during initialization assigned this IP address, this static IP address to our embedded host, so we will ping that IP address only, and this IP address is 192.168.1.121. So now let us hit the enter button and see what happens. Great, you can see it is working perfectly. We are able to successfully ping our board, everything is working great. So thanks for watching. See you in the next lecture.